LeetCode Problem 6, Zigzag Conversion. Sounds like quirky text formatting, but under the surface, it models real-world patterns used in data compression, signal routing, and display logic. The trick? A straightforward zigzag wastes space and time. So how do we zigzag smartly? Let's dive into the pond and decode it. All right, ducklings, let's paddle through the brute force approach. It's not sleek, but it helps us understand the core mechanics. Let's build it out and see how it works in code. First up, a quick sanity check. If there's only one row, or the string's too short to zigzag, we just return it untouched. Since we need to simulate the zigzag shape, we'll drop characters into a 2D matrix, mapping out the rows and columns as they'd visually appear. To navigate the grid, we'll set up row and column pointers, plus a direction flag to track whether we're heading down or angling back up. We loop through each character and place it right into the matrix at our current position, row and column controlled by our direction. If we're heading down, we keep descending row by row, but once we hit the bottom, we flip and start climbing diagonally. While climbing, we shift upward and right. Once we hit the top row, we flip again and start diving down. After we've dropped all characters into the zigzag grid, we scan each row left to right and collect all non-empty entries. We finish by returning the string we just built, a clean read-through of the zigzagged rows. This method takes big O of n time and O of n space, but that matrix adds bulk. For long strings, it burns memory and slows us down. It's easy to follow, but inefficient for tight systems or interviews. So, how do we ditch the matrix? Instead of filling a whole grid, we can collect characters row by row as we go. Let's build that smarter version. Before jumping in, we recheck our shortcut. If the string's too short or just one row, there's no zigzag to do. Return it right away. This time, we prep an array of builders, one per row, so we can stack characters as they arrive, row by row. To steer through the zigzag, we track our current row and use a direction flag to flip between moving down and up. Looping through each character, we drop it into the builder for the current row, like writing across invisible lines. At the top or bottom, we reverse direction. Otherwise, we shift up or down one row depending on the current flow. Once all characters are in, we stitch the builders together, merging all rows into our final zigzag string. This version also runs in O of n time and O of n space, but it cuts the overhead. For long strings, we get clarity and performance, a great balance for interviews or production code. So far, we've still touched every character one by one. But what if we could skip the zigzag walk and jump straight to the right positions? Let's try a math-driven shortcut. First, the usual exit. If the zigzag has only one row or the string's too short, return it directly. No need to process further. Since we're doing a direct read, we'll build a result string as we calculate the zigzag positions. No grid or rows needed. The heart of the zigzag is its cycle, down through the rows, then up diagonally. That full cycle length is 2 times num rows minus 1. We scan each row top to bottom, and for each one, we pick out the characters that land in that row within each full cycle. Using jumps of the full cycle length, we grab the vertical characters, the ones aligned directly under each column group. Middle rows get a bonus character during the diagonal climb. Its index is mirrored within the cycle. We calculate and grab it if it fits. Once we've found the diagonal index, we check if it's valid and we're not on the edge rows. If so, we add that character to the result too. After all rows are processed and all characters are gathered, we wrap it up by returning the final assembled string. This version also runs in O of n time and O of n space, but it's the leanest and fastest. For scale or interviews, it nails both speed and memory, showing mastery over structure and efficiency. We began with brute force, visually simulating the zigzag in a full matrix. It worked, but wasted space. Then we moved to row-wise buckets, more efficient and easier to manage. Finally, we unlocked a math-first solution. No grid, no zigzag logic, just pure index math. This approach doesn't just solve the problem, It highlights how real engineers optimize for constraints. Whether you're aiming for a top tech job or writing performance-critical code, spotting patterns like this is key. So stay sharp, keep building, and we'll see you in the next challenge.